Alright gang, here we go. This is for Chem 2 Unit 7. We're talking about the ideal gas law. We're talking about, that's about it. And density and molar mass and kind of how we can incorporate all these things. So in the previous video we talked about all these different gas equations, right? We talked about Boyle's law, Charles' law, Avogadro's law, Gay-Lussac's law, and we kind of talked about what this can do to help us predict all these different values for our gases and kind of their properties and how things change as we change one factor, etc., etc. Okay, so specifically, Boyle's law told us that volume and pressure were inversely related to one another. Volume and temperature were directly related, and volume and moles were directly related to one another. So if we combine all these, then we get this idea that our volume is proportional to, is proportional to T times N over P. All right. Now, this is a proportionality, that as our, and this is just combining all of these gas laws, right? And then really, if we add in a proportionality constant, this R value, then we can, instead of making it a proportion, we can make it an inequality, and we get this ideal gas law, PV equals nRT, that we're all used to seeing, and we just multiplied P over here, etc., and then added in that constant. All right, so PV equals nRT ideal gas equation. So what is that R value? So this constant value is what really allows us to make an inequality instead of a proportion. All right, and so here's a bunch of different units for R values. This is kind of an interesting, the constant R is a super interesting concept because it actually appears all over the place in science. A lot of times students' first introduction to R is in chemistry when you're talking about PV equals nRT, but it pops up in thermodynamics, engineering principles, physics, and lots of other cases. But specifically, the R here we call the gas constant. Here's a bunch of here's a bunch of units. Most chemists, will use this one. This is the one that we'll use most of all, because it has the pressure unit of atmospheres, and since we do most of our chemistry on bench tops that are at about atmospheric pressure, atmosphere is our go-to unit for pressure. All right, and so its value is 0.0821 or 0.08206. All right, the other really common one, technically the SI unit value, is this one where our pressure is in pascals, and it's in 8.314. Notice that our temperature is always in Kelvin. It's always using that absolute temperature scale. And then also notice that we can also do it using joules per mole Kelvin. All right, so kind of an interesting idea. But anyway, so these are the terms, especially like this one here, and this one here. These are the terms that you should be familiar with. If you ever get a wild hair and you want to do your pressure calculation in torrs or millimeters of mercury, you might also want to know this one. But really the 0.0821 and the 8.314 are the two important ones. All right, so let's do a practice problem here. It says the Goodyear blimp contains 5.74 times 10 to the 6 liters of helium at 25 degrees Celsius in 1 atmosphere. What is the mass in grams of the helium inside of the blimp? Well, we know that we have PV equals nRT, and so the closest thing that we could get to mass out of this is our moles. So if we can find the moles, then we can easily convert that to grams by using the molar mass of helium. So we'll rearrange this to find moles. So N is equal to PV divided by RT. We just divided that RT over. All right, so the pressure is at 1 atmosphere, so we'll put 1.00 for the pressure. And then the volume here, well, it says right here is 5.74 times 10 to the 6th. All right, the R value, now we have to choose our R based on what pressure unit we used. Our pressure unit was in atmospheres, so that means our R value is going to be that 0.0821 value. And then the temperature, now remember the temperature has to be in Kelvin. They give us in 25 degrees Celsius, so we got to convert that to Kelvin. So we add 273.15, so it becomes 298.15 Kelvin. All right, so this is 298.15. All right. Punch that all into our calculator here. We go 5.74 e to the 6th divided by 0.0821 times 298.15. All right. If you do all that, you should have gotten a really big number, right? And that makes sense because it's a huge volume, right? Times 10 to the 6th volume. So here I got how many sig figs do we want? We want 3 sig figs. All right, so 2.34 times 10 to the 5 moles of helium, but that's not what it's after. It's after grams, so we're going to convert moles to grams. All right, so we'll put moles of helium in the bottom, put grams. Can you see me, or am I blocking it? Oh, man. All right, so we'll redraw this up here. All right, so we got 2.34 times 10 to the 5th moles of helium, right? And we're just converting this. This is old hat now. All right, so moles of helium down here, grams of helium up here. For every 1 mole, helium weighs 4.00 grams. All right, multiply that by 4, and we get 9.38 times 10 to the 5th. And be grams of helium. So that's a lot of helium, 9.38. All right. Yep. So the closest answer here would be this E value, 9.39, and probably just a rounding error. Maybe they used a different R value, or maybe they probably, I see I rounded early right here, so that might have been the problem here too as well. I don't know. Okay. Density of gases. Now the interesting thing is, so PV equals nRT, pretty easy. We can also rearrange the ideal gas equation and use our knowledge of molar mass in order to actually use it to also find the molarity, and use the molarity to find, or not molarity, to find the density, not molarity. All right, I see this capital M and it keeps throwing in molarity on me, but in my brain, that's not quite right. All right. So if we divide both sides of the ideal gas equation by V and RT, we get this, right? So we started with this, PV equals nRT. If we divide by RT, that'll go over here, and we divide by volume, that'll go over here. And so we get this value here, N over V equals P over RT. Now hold this in your head for just a second, and just remember this fact, that if we start with moles and we multiply by the molar mass, okay, that's like saying we have moles, and the molar mass is in grams per mole, right? Some values here, and so the moles cancel, right, and you'll be just left with grams, right? That makes sense. So moles times the molar mass gives us the mass, okay? So N times capital M, they're using this as their molar mass, equals M. So if we multiply both sides by this M value, then the N will turn into a mass, right? And then we just get that the molar mass right here. So mass per volume equals the molar mass times the pressure divided by the R constant times temperature, right? And we know that mass per volume, or mole or grams per liter, okay, is density. All right, so we can use this formula here, density equals MP over RT, all right, in order to calculate the density of our gas, as long as we know the molar mass, the pressure, the gas constant, and the temperature. All right. All right. We can also take this, all right, to find, we can use this idea of the density and just rearrange it in order to find the molar mass. And they've done this, so if we rearrange this equation to rearrange for the molar mass, okay, to calculate that, that would mean that our M is equal to density times RT over P, okay? And remember, density is equal to mass over volume, okay? And so they've taken this, if we plug this value in for our density, we end up with this equation right here. All right, so the molar mass. So we can use either of these guys. So these are really two important calculations. We're going to use this for a lab coming up. So keep track of these in the back of your head. These are important. All right, let's do some practice problems with them. All right, what is the density of methane in a vessel where the pressure is 910 torr and the temperature is 255? So remember, density is equal to MP over RT, right? Density equals MP over RT, just making sure I remembered it right. All right, so we need the molar mass of methane. Well, methane, we got 1 carbon, we got 4 hydrogens, all right? So 12.01 plus 4.04, so we got 16.05. Cool, so 16.05. All right, the pressure is in torr, that's no good, so we got to convert that to atmospheres. So to convert, we got 910 torr. We're going to convert that to atmospheres. So for every 760 torr, we have 1 atmosphere, so we're going to divide that guy there. So we get 910 divided by 760. All right, we get 1.19736. 1.19736. So we'll plug that in here, 19736. So that's our pressure for our atmospheres. Our R value, since we used atmospheres, is the 0.0821. And then our temperature has to be in Kelvin, and they were nice enough to give us that as well. So 255 Kelvin. All right, so we'll take all that here. So 16.05 times the atmospheres that we calculated before divided by 0.0821 times 255. We get 0.9179. And how many sig figs do we want? We want, this has 2 sig figs, so we have to have 2 sig figs here. All right, so 0.92, and since it's density, it'll be in grams per liter. All right, and so therefore A is the right answer. All right, okay. One more here. It says, what is the molar mass of an unknown hydrocarbon whose density is measured in 1.97 grams per liter at STP? All right, so we take our formula, the density equals MP over RT, but we want to find the molar mass, so we're going to rearrange it to find molar mass. So molar mass is equal to RT times the density over pressure. All right, so our R value, okay, is, well, we can really choose whatever because it says the pressure value is at STP. So we'll just use atmospheres because that's what we're good at. So 0.0821, all right, times the temperature. And it says it's at STP, so that means at 0 degrees Celsius or 273.15 Kelvin, all right. And then the pressure, times the density, don't forget that part, that's important, 1.97 grams per liter. And then the pressure value at STP would be 1.00 atmospheres, all right. So we'll take 0.0821 times 273.15 times 1.97, and we get 44.17846. Okay. How many sig figs do we want here? We want 3 sig figs, so it becomes 44.2. And we're doing molar mass would be grams per mole. So that's closest in value here. Probably what happened is that they don't use the 0.15 for the Kelvin, would be my guess. Or maybe they used, it might also be slightly different if you use 0.08206, or it could be slightly different because they might use the Pascal value instead. Who knows? But that's primarily it for ideal gas law. Now, the one more thing here that we need to talk about is how to use the ideal gas law with our stoichiometry. So this is going to be nice because we're going to go back to these chemistry skills that you've already mastered, okay? And we can use our volume and these gas data values in order to convert between using PV equals nRT and balanced chemical equations in order to be able to find out how many, reactants or products we're going to need or make with our reaction. Okay, so we can use the balanced chemical equation to tell us the moles of a reactant and then figure out the pressure and the reaction, or so on and so forth. So essentially this just adds another thing to our roadmap, if you can remember that far back. It's been a while since we had our roadmap, but essentially that's all we're doing here. All right, so we're going to do a practice problem here, and it says silver oxide decomposes when heated, and here we go. We got Ag2O is decomposing, so it forms 4 silvers and 1 oxygen. It says if 5.76 grams of silver oxide is heated and the O2 gas produced by the reaction is collected in an evacuated flask, what is the pressure of the O2 gas if the volume of the flask is 0.65 liters and the gas is temperature 25 degrees Celsius? So we need to find, overall, we need to find the pressure of the O2 gas. All right, so we know pressure is equal to nRT over V. Okay, so let's see what we've got here. We've got volume. Volume's right here. It's the 0.65. Okay, we've got temperature. It's right here. Obviously, we need to convert that to Kelvin. Let's do that now before we forget. So that'd be 298.15 Kelvin. All right. We have our R value, right? That would be 0.0821 since they want us to give us our answer in atmospheres. All right. So all we need is the mole. So if we can figure out how many moles of O2 gas we form, then we're good. All right. Well, we can do that. So we know we have 5.76 grams, all right, of silver oxide. So 5.76 grams of Ag2O. Okay, and we're going to be converting that into moles of silver oxide, right? Because we need to use that to use the mole ratio to get moles of oxygen. All right, so we'll set up our thing here. So we got grams of Ag2O here, moles of Ag2O here. So for every 1, so now we got to figure out the molar mass of silver oxide. So we got 2 silvers and 1 oxygen. All right. So this is where I should have had my periodic table pulled up. To start, periodic table. All right. Because I don't have silver memorized, so I don't use it that much. Oh man, this periodic table is really tiny. I can't read it. Oh my gosh, why would they make it so small? All right, here we go. 107.87. All right. 2 times 107.87 grams. All right, 16.00 for the oxygen. All right, so we'll say 2 times 107.87 plus 16, and we got 231.74 for our molar mass, 231.74 grams per mole. All right, so 231.74 goes there. All right, so now we're in moles of silver oxide, so now we got to go to moles of oxygen. Okay, so for every, let's see, 4 moles of Ag2O, we get 1 mole of O2. Right, and I got that from our balanced chemical equation right there. Why did I write 4? It's 2 moles. All right, and so that's going to get us to our moles of O2, which is exactly what we wanted. So we'll take our 5.76 divided by 231.74 divided by 2. All right, and we get 0.01243 moles. 0.01243 moles of O2. All right, so there's our moles of O2. So now we just plug everything in. So our pressure is equal to the moles, which was the 0.01243. Our R value is 0.0821. All right, our temperature value we already found was the 298.15. All right, and then finally the volume is this 0.65 liters. Okay. All right, so we take our 0.01243 times 0.082821. I'm struggling with my calculator. Times 298.15 divided by 0.65. I got 0.468. How many sig figs we want? We want 2 sig figs because that volume. Okay, so it would be 0.47, and it would be in atmospheres because that's the R value we used. 0.47 atmospheres. So that's our answer right there. All right, so that's about it for this video. We did lots with ideal gas equation and stuff like that. Do your homework problems. Let me know if you have any questions, and I'll see you on the flip side.